Okay, let's start. So this course is about deep learning. And I'll start with some course overview today. So here's my intro. I'm an assistant professor in computer science department. And I did a PhD in Georgia Tech in the US. And I'm conducting the research on various areas, including deep learning for computer vision and natural language understanding and generation, and also some HCI aspects such as like human-computer interaction, including visual analytics and data and information visualization. And also I'm doing some text and social media or data mining applications as well. So so here is our classroom that we will meet every Monday and Wednesday throughout the semester. And also our class starts at 5 p.m. And although I think on Monday it will it's shown as starting from 5 and ending at around 6:50 or so, and then also on Wednesday it will end at 5:50, I think. But I'm proposing just to have the equal length lecture on both Monday and the Wednesday. So this is kind of my slightly different class hours. So is there any kind of problems or issues that you guys have? So anyone is not who is not okay with this schedule? Okay, then we will go with this schedule. And also not this week, but next week on both Monday and Wednesday, I'll be out of town to attend some conference, and so I'll have to cancel our class, or I'm trying I'm seeing if some of my students can cover our class, but in case I have to cancel the class, and then in the following weeks, not in the next week, but after that, it may extend up to 6:30 p.m. for about 10 classes. Okay. So I did a quick math, and then having additional 15 minutes, and then 10 times of it, and then it will cover like a week worth lectures. Okay. So I hope everyone is fine with this. Okay, and just in case you wanna visit me, then you can just ask me any questions at the end of the class or before the class. But if you want to visit me personally, and then my office is located in the 5th floor in this building. And the room number is 502. And then I think many of you have already the slides, and I sent the announcement email only this morning, and through the Blackboard. So anyone doesn't know Blackboard? Is there anyone who doesn't know Blackboard? So it's kulms.korea ac.kr, right? Okay, so all the class materials, mainly including the slides and some homeworks and some announcements, emails, all of them will be posted in this website. Okay. Okay, and the goal of this course is to study deep learning in detail. Okay, and as announced in the syllabus, this course will be run in the form of a flipped class. Okay, so basically every class, I mean, this is your kind of a homework or self-study by watching one of the most famous deep learning video lecture called the Stanford CS231N, which is focusing on the computer vision. But throughout our class this semester, I will also cover some other applications and techniques used in other than computer vision. And then this is the course website that contains the video lectures and also class slides. And during our class, where we meet like this every Monday and Wednesday, I'll basically take questions from you guys through some online Q&A board where you can just freely post your questions regarding what you studied from these video lectures. And that website is slido.com. Let's see. Okay. So this is the website that I'm talking about, the slido.com. And you can even you can ask the questions even now, and then it will ask some access code, and then it will always be KUDL. I'm not sure if it's case sensitive or insensitive. Okay, it is not. Okay, so once you go to this website and entering this access code of KUDL, which is standing for Korea University Deep Learning. Okay, and then you will see this kind of board where you can just post any questions, or maybe you can just say hi here, and then it will be updated in real time. And then you can also vote some of these other questions, and then it will be always ranked in a decreasing order of this voting count. And so so the most voted one will be handled with the priority. Okay. And also, so back to this slide. And in the beginning of every class, we will have the 5-minute quiz. Okay. So it will be also done by entering some website. I'll just let you know about this website in the next class. But so once you go to some website, and then you put your name or student ID, and then just answer a few simple questions. Okay. And then that will be that will be reflected into your final grades, of course. Okay. And then so these are the homework until the next class. Okay. Until this Wednesday. Okay. So each class is about an hour or maybe 70 minutes long. Okay. So. And also, for your information, this CS231N, this course is for a graduate level course taught in Stanford. Okay, so it's already quite a demanding course because you guys are mostly undergrad students. So, and also at the same time, you guys will learn additional or some particular topics in more detail among what we studied from this online lectures. Okay, or I will cover some additional kind of topics as well. And so basically this course will be quite demanding course. Okay, so I heard that some students who took this exact same course about a year ago, 2 semesters before, some students said that this course is like a 9 credit hour course. Okay, because you have to teach like graduate level courses by watching these video lectures, and then you guys also have to understand what I explain during our class. Of course, this class, I mean, our session will be mainly utilized to handle or address your questions that you had by watching these videos. Any questions so far? Okay. And then this is an optional textbook. And these are some of the prerequisite background knowledge or courses that I assume that you guys are familiar with. So you guys have to be familiar with Python programming. Okay, so most of the deep learning programmings are done in Python, and also we will also utilize some kind of particular deep learning libraries on which is used on top of the Python language. Okay, so you have to be familiar with the Python and also NumPy libraries, and also maybe scikit-learn as well, which is machine learning libraries provided in this Python language. And also we will mainly utilize deep learning libraries called the PyTorch. Okay, so there are two major deep learning libraries called the TensorFlow from Google, and also PyTorch. Okay, so I think this one is much easier than TensorFlow, especially when dealing with the sequence data involving RNNs or recurrent neural networks or long short-term memory. And so we will mainly use this deep learning libraries. And of course, again, this library is written in Python, so you will just import this library in Python, and then you will use this API or functions provided by these libraries. Okay, and then also this course is utilize quite a lot of backgrounds in linear algebra, and also some of the calculus, mainly using a chain rule and the derivative and so on, and then probability and statistics, and also most importantly, I assume most of you guys have some decent background on the machine learning. Okay, like supervised learning, unsupervised learning, and regression classification, and maybe regularization, overfitting, underfitting, and bias, variance, and ensemble modeling, and so on. Okay, so this course, in terms of our class hierarchy provided in this computer science department, so this deep learning is kind of on top of other prior courses, including artificial intelligence and machine learning. Okay, so I assume you guys have some good amount of background on this machine learning. Okay, so let me do some quick polls. So can you raise the hand if you took the artificial intelligence course offered in this? Okay, great, about 70%. And machine learning? Good. Data science? Okay. Who has already some background on deep learning? Okay, who currently do some projects or some research on deep learning? Okay, don't be shy. Okay, good. So these are some of the list of explicit topics that I assume that you guys have some backgrounds on. Let's see. And these are some course schedule. And here's the grading policy. So we will have maybe 3 or 4 times of one homework involving some programmings, and also just handwriting kind of exercise problems where you have to derive some equations and so on. And then we will have exam on midterm and final. And this one also includes the term project. And as I mentioned, we will have a in-class quiz and class participation. So you can just post your questions online, as I mentioned, in the slido.com, or you can just freely raise your hand at any time and then ask any questions. Okay, and then those class participations are based on your kind of active participation, such as asking as many questions as possible and so on. And don't underestimate this aspect. Okay, so I often see that many of the students are around the borders of your final credits. Among the A plus A and B plus B and so on. And then depending on these participation or how much I remember each students, I actually raise some of the students to a higher grade and lower some of the students' grade into a lesser grades. Okay, and then although I'm not going to check frequently, but these attendance will be checked sometimes. And then if you miss one class, and then among the 100 points in total, you will get 0.5% deduction on your total points. Any questions so far?
Yeah, here we will have quiz every class, right? Like every class. That's kind of like
it's not guaranteed that we will have a quiz every class, but mostly.
Yeah, but that's I guess it's so many quizzes with only 5%. I mean, the grading.
Yes.
Okay.
It will be mostly quite simple ones. Although, it will be simple if you studied properly the video lectures. But most of these questions will, each quiz will be composed of maybe around three questions, and they will be just a simple kind of a multiple choice type of questions, or kind of some kind of questions of filling the gaps.
This is not a very related question, but do you also teach this class in first semester next spring?
I don't think so at this point. It will be offered annually, I think. Although I'm not sure. I mean, if some other professors may want to open the same class in the other semester, but in my case, I don't think I can open this same course in the next semester. Okay. Any other questions? And 그 저기 질문을 한글로 해도 돼요?
강의는
네. 3개씩 들으면 참 좋을 것 같은데 그러지는 않고요. 일주일에 1.5개 정도라고 생각하면 돼요. 지금 첫 주라서 이 사실 좀 3개 정도 렉처는 이게 사실 딥러닝의 좀 전초전이거든요. 그래서 사실 나 스스로도 여기를 좀 많이 다루지는 좀 않으려고 해서 최대한 좀 빨리 보려고 하는데, 일단은 뭐 또 학기 초가 그래도 시간이 좀 많이 남을 테니까 그래도 좀 그때 좀 그렇게 초나가 많이 원래 안 오는데 하여튼 한 1.5개 정도라고 생각합니다. Okay, so on average, I mean per week, you will have to watch maybe 1.5 classes. I mean video lectures, which is about maybe close to 2 hour worth, I think. Because one video lecture will be around 1 hour and 15 minutes or so. Any other questions? Okay, then So again, you have to watch these courses, I mean video lectures, and then be prepared. You have to be prepared for the quiz, okay? And also the quiz will be done in the beginning of the class. So if you are late, and then you have no chance to take the quiz. Okay. So deep learning. So this is a little bit less academical terms. So in many of these academic kind of papers, I mean, research papers don't use this term, okay, deep learning. So when I first submitted deep learning related papers on my own, I put this in the title, and then it got rejected. And I suspect that was the one of the main reasons why my papers were rejected. But anyways, so it's a kind of a buzzword, or a kind of a less academic or kind of a casual terms. And then instead of it, we often use deep neural networks. Okay, deep neural networks. So it's basically stems from or rooted from this artificial neural networks, which was invented maybe several decades ago. Okay, and then let's see. Deep learning or deep neural networks looks like this. Okay. And then it has the this kind of input layer, and then some of the output layer, okay. And then in the middle we have some hidden layers, okay. So in this particular case we have one hidden layer, but in this in the second example we have two hidden layers. And then if we stack more and more layers, maybe up to several tens or several hundreds or even thousands, okay. And then we stacked a lot of layers, and so that is called the deep neural networks, because we kind of stacked these layers quite deeply, okay? And then what is this input and output? So let's just look at some of these examples. So if you want to classify a given handwritten image, which is given in the form of this bitmap. Okay, so it is just a handwritten image of digit 1, okay, and then to computer, or as a kind of digital forms. So it will have some resolution, or basically the size of this image. And then suppose this image size is 28 by 28, and then at each pixel it will have some value ranging from 0 to 1. I mean, it's just a normalized value. And usually if we handle the color images, and then we have 3 channels of red, green, and blue, right? And then it's like 3-dimensional cube, right? So 28 by 28, and then we have 3 channels of maybe red, green, and blue. And each of these values will be typically ranging from 0 to 55, right? Okay, so these are the numerical form, or kind of a numbered form of this given input image. And then if it is a grayscale, and then we can just utilize the average number of this RGB, like 3 channels numbers, and then it will still have the range of 0 to 255, and then we can normalize it into 0 to 1, and then we will obtain this, right? And so if it is a black, and then it will have larger values at the corresponding position, okay? And this is the input, and then it has again the resolution or the size of 28 by 28, right? And then it should be given to our neural net as an input, right? And so those nodes in a particular layer is corresponding to a particular scalar value contained in our image, right? And so here, this is a 2-dimensional kind of form, right? 2-dimensional array as an input, but we can typically just chop them vertically or horizontally. And then let's say we chop them vertically, and then just to move these. Yeah, at the bottom of the first column, okay, and then this guy to the bottom, okay, and then we will have a long and thin vector or one-dimensional array by rearranging these two-dimensional arrays, right? And then in total we have 84 numbers, which is 28 by 28, right? And so that will form our input layer, okay? Okay, and then if we want to classify this guy into a particular digit among 0 to 9, okay, and then we can design our neural net so that we have 10 different output nodes where each of them is corresponding to one particular digit value, okay, and then through some functions done in these layers, including these hidden layers, okay, and then given a particular input vector, and then we will obtain a particular output vector, and then if we want to classify a given image into one of these 10 digits, and then we can just simply pick up the largest, the digit that has the largest values, okay? So that way, so input dimension or the number of nodes in the input layer is determined by our input data, okay? If our image was 28 by 28, and then it will determine the number of nodes in the input layer, right? And then the output layer, the number of an output layer, number of nodes in the output layer is determined by our task goal. So if we want to classify each handwritten digit image into one of the 10 digits, and that's why we have to have 10 different nodes, okay? And then if we want to classify this one as maybe the digit written by either men or women, okay, and then we have to classify one between the two, right? So in that case we will have two output nodes, okay? Or if it is a binary classification, we can just simply have one single node, okay? But anyways, so input and output layers are determined that way by our task goal and the input data and numbers basically contained in our input data. But in the middle, how many layers we will have, and then how many nodes we will have within a particular layer is completely dependent on our design choice, okay? So if we want to have more complex complex neural networks, and then we can add more layers so that our function can do more complicated things, okay? Okay, then okay, someone tested this word. Okay, so again, if you have any questions, during our class, and then feel free to just post your questions. So this website is quite insightful, and you can actually have fun by playing with these neural nets. Okay, so in this case, you can actually change your designs of your neural networks, and also you can also change your task goal as well, just like classifying the same input handwritten digit images into one of the 10 digits, or one of the genders of the person that wrote this image, okay? Okay, so in this case it's a classification task. So here we have a choice of choosing, selecting either classification or regression. So both of them are kind of a supervised learning, right? Supervised learning. And classification is predicting the discrete or integer or categorical variable, just like a digit among 10 different digits. So in those digits, there is actually order, but in the case of men or women, there is no orders, right? So in that case, it is a categorical information, right? And in case of discrete variables as our target variable to predict, the example will be like, suppose you want to predict a person's blood pressure into low or medium or high level. Okay, so in this case, less than maybe 80 and 81 to maybe 120, and this one is 121. Okay, so in that case, so we want to classify a given person, I mean based on his or her feature information like height and weight, and maybe the location of his or her residence and so on. And then we want to classify one among them, and then these values are actually ordered one, right? So these are not called the categorical variable. So this is a discrete, but it's an integer kind of variable, because integer is a kind of discrete, and also they have particular orders, right? But anyways, and then regression is to predict the real values, right? And then, okay, so we set the classification, and then in the case of classification, we assume the two classes, and then these are the given training data, right? And then the x and y axis are the two features that we are given. So if we want to represent a person's feature vector in terms of his or her height and weight, and that will be x and y axis respectively. Okay, and their labels are represented by those colors. Okay, and then we have, of course, two input nodes, right? Because we are originally given the height and weight, right? But what about these? Okay, what about these? So we can turn on additional input nodes, right? But all these input nodes are kind of derived feature values from the original two of these original feature values, right? So one of them could be x, the first feature value squares, the second value squared, and the product of them, and then sign, and so on. Okay, but this one is a kind of more kind of standard situation. And then, yep. So in the middle, I mean, okay. So this is the output node where we have only one node, because we are doing the binary classification, and the binary classification is represented a single scalar node. Okay. In the case of binary classification, what is the most basic method that we use? Can you tell me any kind of binary classification method? SVM or simpler one? Logistic regression, right? Logistic regression. So logistic regression is giving the scalar output, but that scalar output is actually computed from the sigmoid function, right? Sigmoid function that has the range from 0 to 1, right? And if that value is shown to be larger than 0.5, and then we classified it into positive class, or if it is less than 0.5, and then we classify it into negative class, right? So so this one is a scalar output node. Okay, one single node, which is kind of a really enlarged kind of version, and then these two are our hidden layers and the number of nodes within each layer. Okay, then so in this case, I just completely removed, discarded any hidden layers where we only have an input and output layers. And then in this case, so this one is the output while the training is being done. Okay, and then how we read, or the way we read this kind of output is, so those actual dots or point with the particular color is our training data, Okay, and then in the background, the colors are assigned gradually or smoothly, right? And those colors are the predicted value from our learned neural network. So in this case, consider maybe some point, maybe over here, and then it will be classified as what? Positive one, or this orange one, right? And if we are given the test point around here on the right bottom, and then it will be classified as the blue one, right? So, so in this case, suppose we are given the test point over here, and then the prediction value is blue one, but as we can see, the training data around it will all have the orange one, right? So those regions are, clearly those misclassified regions, right? So again, how we read this graph is the actual points and their ground truth label that are given during the training time. Okay, these are actual points are the actual training data, and at the same time, the background color is representing at any given point our prediction results are shown as this color. Okay, so this one is clearly the wrong kind of case where we couldn't properly learn their classification boundary. And then is there anyone who maybe studied the Andrew Ng's machine learning Coursera course? Coursera course? Not many? Okay. So in this particular case, because we didn't have any hidden layer, what is the actual model that we have in this case? So in this case, we have two input nodes, right? And then we have one output node, and then we have two input nodes, which is corresponding to height and weight. And then, those edges are representing some linear kind of combination of maybe AX1 and plus BX2 and plus C, right? And A, B, and C are those parameters that we want to learn, and these are the parameters being learned while this neural net is being played like this. Okay. Okay, and then after this, as I mentioned, this is a classification problem, and if we have no hidden layer, it's just equivalent to the logistic regression that performs this binary classification. And then what is the nonlinear function, or the the function that we go through after getting this linear combination of the input? That is called this sigmoid function, right? Sigmoid function, right? Let's see. How does the sigmoid function look like? So this is something like this, right? So it has a few different names like logistic function and maybe sigmoid function and so on. So this is the function that we use in the logistic regression, right? And so after getting AX1 plus BX2 plus C, okay, and then this one will be used as an input to the sigmoid function. So if it was 3, and then it will have this, and then the function output of this sigmoid function will have this value. Okay. Okay, and then if you studied well about this logistic regression and maybe support vector machine or any other linear classifier, and then this one being equal to 0, and that is our classification boundary or decision boundary, right? Decision boundary. And that is when we give the input as 0 to this sigmoid, and then sigmoid output is of 0.5, and then that means like 50% being the positive class, which means that 50% being the negative class, which is like a 50-50 situation, right? And so in this case, yeah, so it is like, yeah, suppose A1, A2, A, B, and C are 1, 2, and 3. And then it's like x1 plus 2, x2 plus 3 equals 0. And then let's just change it as x and y. And then we can just draw an x and y. And then y is something like this, right? So it's like this kind of decision boundary, right? Right? So if it is above this decision boundary, and then we classify it into positive and then negative if it is below that line, right? And then this decision boundary, if we didn't use any kind of internal hidden layers, and then yeah, this linear output is just passing through the sigmoid and then giving the final score of our prediction score, and thus our decision boundary is this straight line, right? So that straight line cannot maybe separate these nonlinear kind of decision boundaries, right? So if someone remembers how we simply handled this kind of problem by still using the linear classifiers, so that we can handle this nonlinear decision boundaries. And then we can actually use some feature augmentation or adding kind of additional features, yeah, computed by the original features. So for example, if we just add those two, which is just yeah, converted version of the input features. It's just simply height squared and weight squared. And then if we add those two as an additional features, and then now we will have 4 different inputs from the perspective of our model. And so it's like x1, x2, and then we have x3 and x4, right? And then actually this x3 is x1 squared and x4 is x2 squared. But yeah, it doesn't matter from the perspective of logistic regression. It just handles or takes the 4-dimensional inputs, and then it has the freedom of assigning different linear combination weights, right? But anyways, if we augment our features that way, and then I hope it gets trained. But yeah, in principle, it should be trained, but it doesn't seem so, right? Right? Okay, and then let's do some challenge. Okay, so initially it should have used a sigmoid. Okay, so that's yeah, when setting it as a sigmoid, and then it is equivalent to the logistic regression. Okay, so in that case, let's try once again. Okay, so it seems to be quite hard to just properly learn the decision boundary, although we know it should be able to be learned, right? And why? Can we represent the decision boundaries like the circle in order to handle that previous case when using x1 squared and x2 squared? Okay, like ax1, bx2, cx3, and dx4 plus e. Okay, so this is kind of our decision boundary. Although, yeah, that will be passed into the logistic regression, and then depending on whether they are negative value or positive value. So this is the point where we have the probability more than a half or less than a half, right? So that way, this linear equation being 0 is our decision boundary, right? But anyways, now this x3 is actually x1 squared, and x4 is x2 squared, right? And then how do we kind of represent that decision boundary of a circle, right? It is simply 0, 0, and 1, 1, and then maybe minus 2, and then x1 squared and x2 squared, and then 2, right? So it successfully represents the decision boundary of a circle, right? it can even represent kind of an ellipse and so on, right? So we know it should be learned, but somehow it is not being trained, right? Okay, let's see. Yeah, let's just play with this neural nets by changing some of these activation, something called the activation function. I thought it should be trained. Let's see. Why is it not being trained?
I think maybe you want to reset it first.
Oh,
Yeah.
really?
See the width.
Ah, I see. How do you reset it?
Beside the pause button.
What's that?
Beside the pause button.
Pause button. Ah, okay, yeah. Okay. Did I reset it? Okay. What will be the problem?
I think it's just a picture that doesn't change because it is converging. Like
The loss is 0.
yeah.
So it looks like it's properly learned the parameters assigned to x1 squared and x2 squared, and almost 0 on the original x1 and x2. But we don't know what the bias value is, or here the e value. I mean, we cannot check if that e value was properly trained or not, because it doesn't explicitly show that. Okay, it should work, but I don't know why it doesn't work. So it could be your first homework. Okay, playing with it, and then succeed on properly training it. But anyways, let's just change the designs like this. Maybe I add more hidden layers and so on. I don't think I need it. Does it change at all, that figure on the right?
No.
No? Okay. Okay, it is now reset. Let's try again. I don't know. Yeah. Okay, so you already learned how difficult it is to train our neural nets. Okay. So I'll try also more. When I get back. But sometimes even for these simple settings, you can easily find that it is quite difficult to kind of train these models, and kind of the most difficult version is like this. Okay. So this one has really complex decision boundaries, and then because it is really complex, it should have many hidden layers. Okay, at least it seems to be much more dynamic than before. Okay, so so in this case it is even more difficult, right? So this data set is called, this specific this data set has a specific name called the Swiss roll data. Okay, so you know the Swiss roll cake, right? So the jam is having that kind of shapes, right? So it is called the Swiss roll data, and then machine learning researchers have played with that data set for maybe at least several decades, I think. And so if you search for like, so it is really difficult to succeed in training that Swiss roll data and properly learning the decision boundaries. So so if you actually search for the playground, TensorFlow playground, Swiss roll, and then someone actually posted some of the proud result of their own that succeeded to properly learn these decision boundaries. So in this guy, his or her design, his or her own design was to use just a single hidden layer, and then maybe 2, 4, 6, 8 hidden layers, and instead, and also he also used a lot of feature augmentation, right? And then also maybe some other guys. Okay, so this one seems to be much dynamic. Okay. Oh, looks good. So in that case, this guy used maybe 3 hidden layers in the middle, and then these many number of nodes. Okay. Okay, and then so in this particular case, let's think about additional kind of aspect. Okay, so in this case, what would be the training accuracy? What would be the training accuracy in this case? So again, I mentioned about how to read this kind of result, right? Training data with an actual point and their colors and their background as the predicted value, right? And at least given those blue points and the red points that are actually given, right? Those colors are matching the background color, which seems to be like all the data being classified correctly, right? So in this case, the training accuracy will be 100%, right? But what about the test accuracy? Do you guys expect it to have like maybe 100% accuracy or maybe close to 100% accuracy? So in this case, so these are the limited number of training data that we are given, right? And then suppose we are given another blue point around here. So from this kind of pattern, we can we have no problem kind of in extending those lines more and more, right? And then we can imagine some of the test point which is not yet seen during the training phase as this point, which is still blue point, right? And in that case, it will be misclassified in our model, right? Okay, so so that is basically the gap between the training accuracy and the test accuracy, right? And minimizing the gap. I mean, in principle, if we use more and more complicated models that has more number of parameters, such as like adding more and more layers and number of nodes within the layers, and then in principle we can kind of represent really complicated decision boundaries given the training data, but we do not know. We do not actually care about the unseen regions like this. Okay, so in that case, how can we? So in that case, the training accuracy will be 100%, and then the unseen data and their test accuracy will be maybe around 80% or even maybe 70% or less, right? So there is a gap between the training accuracy and the test accuracy, right? And then reducing the gap. How can we reduce the gap? So the simplest way is to provide more and more training data, right? Okay, so we can fill out the training data entirely over these entire region, right? So in that case, our training data will cover every single regions in our feature space. So in that case, if we can achieve 100% training accuracy, and then it means we achieve 100% test accuracy, right? But if we, is there any other ways? I mean, how do we reduce the gap between the training and the test accuracy? So that is generally called the regularization, right? Regularization, like L1 or L2 regularization. And also in the case of deep learning, the dropout and the batch normalization and any kind of a normal, so there are many different normalization in these days, and those different normalizations used in the deep learning or deep neural networks are actually working as a regularization factor, which reduces the gap between the training and the test accuracy. Okay. And also, this kind of overfitting to our training data is actually working as a kind of blind side or pitfall that can be utilized by the malicious attackers of our neural nets. Okay, so if you so this term adversarial is quite famous and widely used term in deep learning literature because it's related to generative adversarial networks, which actually produces a lot of interesting kind of generative examples. And then also in terms of security of our neural nets. So for example, if you just develop the deep learning or deep neural network, you trained really well your deep learning so that it can properly work as your kind of auto kind of navigator in your autonomous driving kind of systems. Okay, and then if you just manipulate, I mean, some hackers or attackers may just manipulate a little bit of your car's camera or the input pictures, and then you can easily fool your autonomous driving system so that it can crash into some person or some walls and so on. So that is called the adversarial attack, okay, like malicious attack, okay, and then. So this adversarial examples are also quite on hot and active research areas. And then let's look at some examples. Okay, so this is one of the example posted in the original papers that proposes this adversarial example. And then so this is about the example where you learn or you trained your deep learning so that your model can classify the given image, I mean, into a particular object. So if it is a panda, and then it will classify it as a panda, and if it is maybe desk or chairs, and then it will classify into the corresponding classes. And in that case, so if you just manipulate this image, so that we just add that kind of just a random looking noise, like all red, blue, and green, and so on, in the corresponding pixel positions, and then this is the resulting image. Okay, so in this resulting image, your classifier will classify it as I forgot the meaning of this gibbon, or what is that? Does anyone know the meaning of it?
Monkey.
Huh?
Monkey.
Monkey?
Yeah.
Oh, is it monkey? Okay. So in the case of monkey, it is kind of similar to panda. But there are a lot more extreme kind of results as well. Okay. But anyways, it will classify this still panda-looking images into like a monkey with really high confidence, with 99% confidence. Okay. So there are so many examples like this. Okay. Okay, so yeah, related to this example, okay? So you can think of this point as your original panda, okay? And then slightly moving this point towards the classification decision boundaries, towards that direction. And then by only moving this point with this amount, okay? And then you can, safely just pass across this classification decision boundary, and then you can actually fool your classifier so that it can misclassify it into quite different classes. Okay. So intentionally moving or intentionally changing slightly your input feature vector representation. Okay, in a malicious with the malicious intent, and then that is actually utilized as a adversarial attack. Okay, and also similar to kind of literature in the security, there are many papers that proposes a new attacking algorithm to fool the neural net, and also at the same time there are many papers that proposes kind of defending algorithms against those different attack algorithms. Okay, so it's like 창과 방패 싸움이 뭐죠? 영어로? 창. 네. 창과 방패 싸움 뭐 그런 거 있죠. 네. Any questions so far? Okay, so 네, 이거 팀별. 네. Okay, so I forgot to mention about the details of term project. So I expect you to form up to maybe 3 persons, okay, for your term project. Although, it is no problem to do the term project on your own, okay? Any other questions? Okay, in that case, I can, it's not an admin page. I can log in as an admin because I created this page, and then I can archive it, or I can kind of remove it, okay, if it is resolved. Okay, so back to the intro of deep learning. So you guys have a kind of rough idea about how the neural networks or the deep neural networks looks like. And also, deep learning is a particular category within the machine learning, and this machine learning is a category within the artificial intelligence, right? So what's the difference between the machine learning and the artificial intelligence? Or, what are the approaches corresponding to this star regions, which is artificial intelligence but not machine learning? So what's the difference?
Rule-based chess machines.
What's that?
Rule-based chess bots.
Yeah, right. So this star region is corresponding to the rule-based thing, right? So you just develop your own algorithm, right? Yeah, so without any kind of previous examples or training data, right? And then the machine learning is, assuming that the model is just it is learned. Yeah, it is just a general purpose learner or machine learning model, just like a linear regression where we have the coefficients that are not yet learned. And then if we give training data, and then those parameters are adapted or adjusted so that it can fit your training data, right? So this guy assumes training data, and this learning means learning from the training data, okay? And then deep learning is also a kind of machine learning, but this is a particular machine learning kind of model of these neural networks or deep neural networks rather than other machine learning models like linear regression, logistic regression, k-nearest neighbor classifier, support vector machines, and then maybe decision trees and gradient boosting or random forest, and all these non-neural network machine learning models exist, right? And then these algorithms are corresponding to this region. And then if you select the machine learning models as neural networks, and then that will fall into this category. Okay, so the factors for a recent success of deep learning, three main aspects actually play the main role of bringing big success in deep learning: big data and improved training algorithm, like this. And then you will learn about the gradient vanishing problems, just like the previous example where we had a hard time in training really even simple kind of ring type classification boundaries, right? So it was not properly trained, right, for some reason, right? So so that way, so we need additional kind of advanced techniques so that we can properly train our model. And this regarding the issue of this big data thing, let's see if I have, maybe not. Okay, so there is a kind of well-known and widely used graph. So suppose this x-axis is number of training data, okay? Y-axis is your test data accuracy, okay? And then if you use a linear regression or logistic regression or maybe decision trees and so on, and then it will be trained like this, okay? So up to maybe 100 or 1,000 data points, and then it can quickly increase the test data accuracy up to maybe 80%, okay? But in the case of deep learning, it has the patterns like this, okay? So if you have a small number of data, and then you will actually be often frustrated by seeing that, okay, so you actually use the deep neural networks with the really complicated and advanced architectures, and then you compare the performance of it against the performance of maybe standard or traditional kind of machine learning models like maybe decision trees or random forest and so on. And in many applications, other models than the deep neural networks actually often performs much better than the deep neural networks, okay? So that way, I had the exact same experiences. And then, so I was not kind of, I was kind of confused. And why, I mean, is it really a good algorithm or good model and so on? But the deep learning is really shining when you have really large number of data, okay? So this is the about the hardware. So if you just train or use your deep neural networks on the CPU, and then even if you buy maybe several $1,000 worth CPUs, and then it can take around maybe a month or even a year to properly train a particular model using your big data. But if you happen to train your model using this GPU, which is only maybe $1,000 or less than $1,000, and then it can just be trained within a day or maybe within a few days and so on. Okay. This guy, he's not doing much research in these days, but I often call him as Paris Hilton in the deep learning communities. But anyways, and these are the major conferences. If you want to search for some interesting research papers for your own projects, and if you want to study advanced deep neural network techniques, and these are the conferences that you want to look at, okay? And then if you happen to have a publication or if you write a paper and then get accepted, in one of these conferences, and then it may change your life. Okay.
Will there be GPUs available too?
Oh, that's a good question. So we got assigned one single machine that has 4 GPUs. I don't think it will it will suit the needs of all these students. So one possible solution is to use a Kuocw. Okay. So you can search for this keyword of Kuocw. So it's really a GPU cloud, graciously provided by Google for free. So you can use that. And also in some of these Amazon or Microsoft cloud, if you just subscribe using like your student account, and then you may get some free credit for maybe several tens of hours or so. Anyways, I'll also see if there's any other better ways. Any other questions? Okay, then I want to just end with one of the interesting projects or interesting research papers that was published in maybe a couple days ago. Okay, so this is one of the deep learning and computer vision applications where you have the source video where on the top left, that guy is a really expert, dancing expert, okay? And then he dances, and then suppose, okay, so this guy is dancing, and then this guy is just like you, I mean, who is not good at dancing. And then you can just impose a lot of these dynamic movements into that person, with this realistic kind of quality. Okay. It has also some music, but Okay, so you can do that kind of interesting things by using deep neural networks, and that's it for today's class. And let's meet next this Wednesday. And again, please be prepared for your quiz. Okay, and don't get late. Thank you.